In this video, we will be talking about the stereochemistry of alkanes. So in the last video, we talked about alkenes. This one, we'll be talking about alkanes. So we already saw that some molecules and some things are chiral. Chiral meaning their mirror images are non-superimposable. We have another name for mirror images that are non-superimposable. And these mirror images we call enantiomers. So enantiomers are chiral molecules where their mirror images are non-superimposable. So what do I mean by mirror images? So say I have a molecule and it's got 4 different substituents on it. So this has got 4 different substituents on it, so we would call this carbon a chiral center. So say we draw a mirror plane down the center and we take the mirror image of it. So I have the F back here, carbon, the bromine pointing up, the H pointing away, and the Cl pointing towards us. So what this means is there's no way I can rotate this molecule such that I can put it directly on top of each other and it'll match. I can twist it, I can turn it, but there will not be a match. An example of a non-chiral molecule would be something like, say we have a Br, and then we have another H. I'll put that as a wedge. And then we have a Cl. So again, we're going to take the mirror plane and draw the mirror image. So I have the Cl in front, going back to the carbon, the Br pointing up, the H pointing out, and another H pointing out. I can see that if I rotate this molecule around in the plane of the HHCl, if I rotate it around 120 degrees, I can get, so this is a 120 degree rotation, I can get to this original molecule. So this is an achiral molecule, meaning that, as we saw in the previous video, it has that mirror plane, but it also, we can rotate it around and it is not an enantiomer. Enantiomer meaning that it has a non-superimposable mirror image. So how would we distinguish between these two enantiomers? And it turns out that the notation, similar to an easy notation for alkenes, we have a notation for distinguishing chiral centers, and this is called RS notation. So RS notation follows the same Kahn-Ingold prelog rules for designating priority, and we'll see that R comes from the word for right and S comes from the word for left, based on the direction in which we're going when we assign priority. So let's look at a molecule, and the sign is RS notation. So say we have carbon, and up we have iodine, to the side we have Cl, in the front we have Br, and in the back we have H. So again, we would go around, and the 4 substituents around carbon, we would assign them from lowest to highest priority. You can name 1 as your highest or 1 as your lowest. It doesn't really matter as long as you keep track. I'm going to call 1 my highest priority. So in this case, between iodine, chlorine, bromine, and hydrogen, iodine has the highest priority, so I would give that number 1, followed by bromine. Again, priority tracks with atomic number, so we're going down in the atomic number now, followed by chlorine, and hydrogen would be number 4. We're then going to go from 1 to 2 to 3. So I'm going to go from 1 to 2, 2 to 3, 3 back to 1. And I'm going to see whether it goes clockwise or counterclockwise. So if the rotation is clockwise, we call this R. If it's counterclockwise, we call this S. So in this case, we go 1 to 2 to 3. This is clockwise, so we would call this an R, designated chiral center. Now, what happens if the H is in the front? So say instead of this, we have a slightly different variant. So we have the I pointing up, we have the Cl pointing to the side, and now we've switched it. So we have the H pointing forward and the Br pointing back. Again, we would assign priority, so the I would be number 1, Br would be number 2, Cl would be number 3, H would be number 4. We would go around from 1 to 2 to 3 and see which direction we go. 1 to 2, 2 to 3, 3 to 1. It appears to be clockwise. However, since this H is pointing forward, and only if it's pointing forward, we need to do the reverse. So instead of R, we would call this an S, chiral center. Now this works just like E and Z notation. This works for cyclic molecules. So say we have this center here. So I'm going to put a CH3 and an OH here. And remember, there's an implied hydrogen here and an implied hydrogen here. So we already know that we can assign both of these as chiral centers, but now we have to be able to give them R or S notation. So if I'm looking at this methyl substituted center here, we would have a C, and I'll let you go through this as practice. We have a C, and a C. So we can't compare there. We would go one out. We would see that this branch containing the O would be number 1. This branch not containing the O, but eventually containing the O, would be number 2 because it's attached to another carbon. This methyl would be number 3, and this hydrogen would be number 4. So then we go from 1 to 2 to 3. We go 1 to 2, 2 to 3, 3 to 1. So we would say that this center, since it goes clockwise, is R. We would also see that this center is, if you practice this and try it for yourself, you would see that this would be priority number 1. I'll do this in red. So this OH would be priority number 1, this branch would be priority number 2, this branch would be priority number 3, hydrogen would be 4. So if we go around from 1 to 2 to 3, you have 1 to 2, 2 to 3, 3 to 1. This would be counterclockwise, so that would be an S center. So we have an R and an S center mixed into this cyclic molecule. Now there are different ways of showing chirality in molecules, and one of the ways that in the alternative to having wedge and dash bonds, so we can have Fischer projections. So Fischer projections, instead of having wedge and dash bonds, flattens them into the plane of the board. So let's see how to draw a Fischer projection. So let's say we have an H and a C and a CH3 pointing up and a Cl pointing out and a Br pointing back. So the first step in drawing a Fischer projection is we're going to rotate it. So horizontal lines are going to be wedges, and vertical lines are going to be dashes. So we're going to rotate this molecule. I'm going to kind of flatten this we're starting to flatten this into the plane of the board. So I'm going to choose these two to be pointing out and the Cl and the Br to be pointing in. So our horizontal will be wedge bond. So we have an H pointing out and a CH3 pointing out. And then we have a Br pointing up and down and a Cl pointing down. We finally are going to flatten this. So we draw it just with normal lines. So we draw a cross. We have the Br at the top, the CH3 to the right, we have the Cl on the bottom, and we have the H on the side. So how would we determine this as R or S? In this case, I can go back to this. I can assign Br as priority number 1, Cl as priority number 2, CH3 as priority number 3. We would go around in a circle to see which direction it goes, 1 to 2, 2 to 3, 3 to 1. We see it goes clockwise, so this would be R. If we're doing this on a Fischer projection, we see we have Br as 1, Cl as 2, CH3 is 3, H is 4. In this case, remember the H is pointing up. So if we have the H pointing up, what we need to do with a Fischer projection is flip these two. If and only if the H is pointing up. We're basically flipping the molecule around. So we have CH3, H, Br, Cl. Again, we'd have the same priority as before. We have Br as 1, Cl as 2, CH3 is 3, H is 4. And then we go around in a circle to see which direction it goes, 1 to 2, 2 to 3, 3 to 1. We see that it's counterclockwise, and we confirm that this, or clockwise, so we confirm that this is an R Fischer projection, or an R-centered molecule. So what happens if there's more than one chiral center in the molecule? So if there's more than one chiral center in the molecule, we can get a host of different relationships between different variants of the molecule. Turns out that the total number of molecules for a given number of chiral centers is going to be 2 to the n, where n is the number of chiral centers. Now this is the total, but this is the max. So we'll see that there's some molecules that don't have 2 to the n different molecules, but the maximum number of molecules for a given number of chiral centers is going to be 2 to the n. So for instance, If we have one chiral center, 2 to the 1 would be 2. If we have 2 chiral centers, we'd have 4 molecules. If we have 3 chiral centers, we'd have 8 molecules, and so on. So if we have two different, let's examine a case where we have 2 different chiral centers. So 2 to the 2 would be 4 different possible molecules. There's a couple different relationships. We've already seen that enantiomers are non-superimposable mirror images. So enantiomers are non-superimposable mirror images. What this means is that all chiral centers are inverted. Just like if you take a mirror image, it reverses everything. In the case of enantiomers, all chiral centers have been inverted. Now, what happens if not all chiral centers are inverted? And in this case, that would be called a diastereomer. So a diastereomer means that some chiral centers were inverted, but not all of them. So let's look at a case where we have a couple molecules. We have 2 chiral centers, and let's examine the relationship between these molecules. So let's look at this molecule here. So I have a Cl here, and I have an OH here. Now I'll let you kind of determine the absolute stereochemistry of both of these centers on your own, but I'll tell you that this is R and this is R. Now we can imagine that there's 4 different possibilities for inverting these centers. We can invert one, we can invert the other, and then we can invert both of them. So first we'll invert one. So I'll leave the OH pointing up, and then I'll switch to Cl pointing down. Then I'll do the other. I'll invert the OH. So the OH is pointing back, and the Cl is pointing up. And then finally I'll invert both of them so that the, not pointing up, but pointing back. So we have both the OH and the Cl pointing back. Now, if you examine the stereochemistry at all of these centers, we see that anytime there's an R, anytime there's one pointing up, it'll be R. Anytime one is pointing back, it'll be S, and that's coincidental. But what we see is from top left to top right, we go from RR to RS. So we've inverted only one of the stereocenters. So these 2 compounds we would call diastereomers. In fact, all of these around the edge we would call diastereomers. From top to bottom, we go RR to SR, another diastereomer pair. We have SR to SS. We've only inverted one. That's another diastereomer pair. And then in this case, we have RS to SS, another diastereomer pair. However, these diagonals, if we go from top left to bottom right, we go from RR to SS. We've inverted all stereocenters, so this would be an enantiomer pair. In this case, we go from top right to bottom left, we go RS to SR. So this would be another enantiomeric pair. So again, diastereomers is where we're inverting some of the chiral centers, and enantiomers are a specific case of diastereomers where we've inverted all of the chiral centers. Now, what happens if we have chiral centers but the molecule itself isn't chiral? So we have chiral centers but an achiral molecule. If we have a case where this is true, these are called mesocompounds. So mesocompounds are achiral molecules where you have a chiral center. So an example of this would be this diol here. So you can see if I rotate it around, you can see that there's a mirror plane right through the middle of this molecule. So remember, achiral means it has a mirror plane in it. And in this case, an achiral molecule is always going to have a mirror plane in it. Now, what we'll also notice with mesocompounds is this is when we do not get 2 to the n different stereochemical arrangements of a molecule. In this case, we have 2 stereocenters. Now, we do have stereocenters, right? This carbon and this carbon are both technically stereocenters. So we have chiral centers, but the molecule itself is achiral. What we'll notice is we only have 3 possible arrangements for the molecule. So we have one where they are both, we would see that these are both RR. We then have the SS variant. And then we have the RS variant. And we'll see that this, if I were to write, so we've gone from RS, if I were to write SR, this would not be considered a separate enantiomer because I can just rotate this molecule around 180 degrees and I would be left with the same molecule that I just drew right here. So this is not considered a separate stereoisomer of the compound. So we would actually only have 3 stereoisomers of this meso compound. Again, keep a lookout for meso compounds. They are achiral molecules that do have chiral centers. The other thing that to note, and we'll see this much more in the class, is chiral centers can be generated by reactions. We say that reactions that generate chiral centers, we call these stereogenic, and we'll see many more stereogenic reactions in this class later in the semester.